You ever stop and think about what's really going on inside your favorite game? Behind the beautiful graphics and the intense action? Well, it's not just fun and games. It's a constant, invisible war between the wildest dreams of game designers and the tough, physical limits of the hardware you're playing on. So let's pull back the curtain on that hidden conflict.
Ah, yes, the loading screen. We all know it. We've all been there. It's so common, it's basically become an icon for gaming as a whole, right? Whether it's a spinning wheel or a page of handy tips, it's this universal moment we've all shared. But it's more than just a pause in the action, it's actually a clue.
I mean, seriously, just think about it for a second. The combined hours that all of us gamers have spent just staring at these screens must be astronomical. This whole waiting game isn't some feature developers wanted to put in. Oh no. It's a necessary evil, a consequence of a much deeper technical story, one about data, memory, and the raw power it takes to build the worlds we love.
Okay, so where does all that waiting come from? Well, the root cause is basically a data explosion. The leap from old-school, text-only adventures to the kind of photoreal games we have today, that journey is built on a mountain of data that has grown exponentially, and our machines have to climb that mountain every single time we play.
And this breaks it down perfectly. Back in the day, to get the letter A on the screen, a computer just needed to write one single byte to memory. Super simple. But to draw that same letter A as a picture, with a specific font and color and edges, the program has to write data for every tiny dot that makes up that shape. It's a huge jump. Now imagine that, but for every blade of grass, every character, every single object in a massive game world.
So how does your screen actually make the picture? Well, pretty much every screen you use is what's called a raster display. The easiest way to think about it is like a giant grid of millions of tiny colored light bulbs, or pixels. Your computer has the insane job of telling every single one of those pixels exactly what color it needs to be, and it has to do that 60 or even hundreds of times every second. It's an absolutely incredible feat of high-speed data juggling. And for each one of those pixels, there's color. This number, almost 17 million, is the number of possible colors available in what's called 24-bit true color, a standard that really took hold in the 90s. That's nearly 17 million color choices for every single pixel on your screen. The sheer amount of data needed just for color is staggering, and it's a massive reason why our games have so much stuff to load.
Okay, so the game has all this data it needs: models, textures, sound files. Why can't the computer just grab it all instantly? Well, the answer lies in something we can call the memory mountain. It's this hierarchy where, and this is the key, not all computer memory is created equal.
The thing you have to get here is the trade-off. It's always between speed and size. At the very top of the mountain, you've got these tiny, ridiculously fast bits of memory right on the processor itself. A step down, you have your main RAM. It's much bigger, but also slower. And way down at the bottom of the mountain, that's your hard drive or your SSD. It's huge, but in computer terms, it's incredibly slow. A loading screen exists because your game has to physically pull massive files all the way up that mountain, from the slow, big storage into the fast, tiny memory where the processor can actually work with it.
And this quote, it just nails the core conflict. A game running well isn't just about having a fast chip. It's this constant three-way tug of war. You've got the cleverness of the software, how well that software is translated into a language the hardware understands, and then the actual physical limits of that hardware. Programmers are stuck right in the middle of that fight.
But here's the cool part. Programmers don't just throw their hands up and surrender to these limits. Oh no. They get clever. They get crafty. They come up with these ingenious tricks and workarounds. Sometimes, let's be honest, outright hacks to bend the hardware to their will and make impossible things happen. This is one of the most legendary examples. Instead of just slapping a loading screen in your face, the developers of Metroid Prime built the loading process right into the game world. When you shoot a door, it doesn't just pop open. There's a little delay. In that moment, the game is frantically loading the entire next room in the background. The door is just a brilliant disguise for a loading bar. You're still waiting, but you don't feel like you're waiting. Genius.
Now, to really appreciate the artistry of these kinds of hacks, just look at this number. 4, as in 4 kilobytes. That is how much memory developers on the Nintendo 64 had to work with for the instructions that told the graphics chip what to draw. 4 kilobytes. That is absurdly, ridiculously small. A simple text email is bigger than that today. So how in the world did they create these gorgeous, massive 3D worlds like in Super Mario 64 with just 4 KB? Well, the secret weapon was something called microcode.
Basically, Nintendo let programmers write their own custom, hyper-efficient mini programs directly for the graphics hardware. They could load one tiny, specialized tool into that 4 KB of memory to draw water, then swap it out for another tool to draw Mario, and so on. It was an absolute masterpiece of optimization born from pure necessity.
Now, that kind of deep, technical wizardry really defined an entire era of gaming. But while programmers were busy mastering those hacks, the hardware itself was going through a massive change. We kind of hit a physical wall where we couldn't just make a single processor faster and faster anymore. So today, the challenge isn't just about raw speed. It's about managing dozens, sometimes hundreds, of smaller processors all working together at the same time. The game has completely changed.
And to give you a sense of just how much things have shifted, get this. A modern luxury car has around 100 separate microprocessors inside, all handling different jobs. Your game console, your PC, your phone, they're all multi-core systems now. The old era of relying on one super-fast brain is long gone. We're living in the world of parallel computing now.
And this shift forces you to think in a totally different way. For decades, programming was like writing a to-do list for one very fast employee. Do this, then do this, then do this. Simple. Now, it's like being the manager of a massive team. You have to break the entire job down into smaller tasks, hand them out, make sure everyone has what they need, and then make sure they all sync up perfectly at the end. It is just so much more complex. So all this means that the job of a programmer who cares about performance hasn't gotten any easier. In fact, it's gotten way, way harder. They still have to be masters that memory mountain we talked about, but now they also have to master parallel programming to manage that whole team of processors. They have to worry about energy efficiency. They even have to understand how to get a single one of those processors to juggle multiple tasks at once. The burden of making things run fast has been shifted almost entirely onto the software developer's shoulders. And that brings us to the big final question, doesn't it? We're stuck in this kind of arms race, where hardware gets more and more complex, and our ambitions for what software can do grow right alongside it. The programmer is caught in the middle, fighting this battle with cleverness and creativity. But as the systems they build on get more and more intricate, will they always be fighting this uphill battle? Or will we finally create tools and technologies that simplify this constant struggle for performance? The game, it seems, is far from over.